Evening, guys. My name is Sechanze Lewis, Group 1, and our title is Full Basic Accelerated Education Content Generation using Large Vision Models. Basically, in Uganda, we have a large number of refugees, about 1.4 million. And these ones, when they come, they are shifted to an accelerated education program, basically, where they are supposed to cover course around 2 years in just 2 years. Basically, most of them are not well versed with the language that is spoken in the country or in the area they are. And with this, we bring in this photo voice accelerated education content generator with use of the large vision models, and this will help to generate content in visual form, basically in images, on a certain topic and produce that content in an image that is explaining the topic in a story form that is easy to understand, and basically that will favor those of the native language, basically the language that basically they understand. And within this will also is the educators to solve their problem, the pedagogical problem, and we will enable them generate the content to educate these learners, basically. And this will be by passing the content-based curriculum from the National Curriculum Development Center, so that it aids the system in helping educators to create education content. An overview. Basically, these existing large language models like GPTs are transformative, and their architectures are being fundamentally purposed and lack your tasks. This basically lowers our system. Basically, we leverage it by AI for visual storytelling. And the technical reflection, we have the limitations of this text-centric model. These ones like GPTs, that, among others. Basically, their limitations have caused a lot of challenges in creating visual content, and with this, bring in large vision models such as Unicontrol Net. We have Clip. We have so many others. Basically, connecting artificial intelligence to visual logic and 3D environments, using tools like Hugging Face. Hugging Face basically is a platform where one can get open source already trained models. Tools like Blender. This will help in 3D imaging, 3D creating 3D visualizations, and tools like Unity will also help in creating game-based models, game-based visual content. And basically, GitHub and Hugging Face basically will be used for version control and collaboration. And in our project, we shall use Hugging Face basically for getting the already existing models, so that we reduce time that would have been wasted in training models for visual content generation. Paper one, the ControlNet all-in-one control text image diffusion model. Basically, this is a text-to-image model. Basically, this existing text-to-image model lacked the detailed control, and this ControlNet adds the multi-control via two adapters, and it's efficient, composable, and improves on the existing models. Basically, this one comes in as a all-in-one under the idea of multimodal fusion, where it combines a number of models. We shall say text-image diffusion models, large language models, large vision models, to come up with one, the unique control net. So this is its architecture from the paper. Basically, they shall see the encoded prompt, and this is the noise encoder. This is the decoder. So here we shall add content. Then here is the local control adapter. Basically, this is one of the adapters, and the global adapters. Basically, the global adapters where text tokens are entered, and the global condition in global conditions to extend prompt. The domain specific problem here. Basically, the field of controllable content generation moves beyond the basic text to image creation to large vision models. It focuses on producing images with precise fine-grained control over their spatial layout, semantic content, and artistic style. And basically, this enables structured and specific outputs, which is crucial for applications like therapeutic storytelling, custom visual aids. Okay. In this case, accurately conveying particular scenarios, details, and emotions is essential for effectiveness. Basically, this is the architecture I came up with for the unique control net pipeline, and it includes the base diffusion model. This is basically for visualizations of visual images with an encoder, the middle block, and the decoder. This processes noise and they interpret the extended prompts via add and concatenate operations. And the architecture features this architecture basically features a local control adapter for pixel level conditions like edges and depth, and global control adapter for managing style and text embeddings. And together, these adapters generate extended prompts to guide the base model, enabling flexible, high-quality image symbols. So, the input conditions we have under the unique control adapters, we have the local control adapters that works with the local conditions, and the global control adapters that works with the global conditions. Basically, keep image embedding. We also have the text prompt. Basically, this will be for the user's prompt or message prompt, so that the model creates visual images. Then we have the noise predictor unit or unique control net, basically, and the output will be an image faithful to all inputs. The other model, the second paper talks about the segment anything model. Basically, this model is designed and trained to be promptable so that it can transfer zero shot to new image distributions and tasks. And we evaluate its capabilities on numerous tasks and find that its zero shot performance is impressive, often competitive with or even superior to pre-or fully supervised results. The domain-specific problem, basically the problem of general-purpose visual understanding and isolation, focuses on open-world promptable segmentation, identifying and isolating any object based on user intent. Based on user intent, this enables dynamic image querying or for storytelling, structured output aligning with ability to handle high-level ambiguous information. Basically, this model, just for the case, creating maybe a nursery-based curriculum for students in the nursery teaching, basically the young ones. A model will enable an educator to create education content. Say it will enable a teacher can maybe enter a specific image or a specific text, maybe of a dog, and this model will be able to identify or to create an image of a dog in that setting. The segment and the computational problem architecture, it involves three-part system, an image encoder to process the image, then a prompt encoder to process the user input clicks, boxes, inputs that clicks, boxes, and text, and a mask encoder that combines information from both encoders. This is the segment and thin model. We have the lightweight mask encoder. We have the prompt encoder where the educator enters a prompt. We have the image encoder that processes the images. So this is the architecture of the segment anything model. And under the processing phase, we have the spatial. We have different prompts. We have the spatial prompt, the text prompt, and the mask prompt. And the spatial prompt connects with the prompt encoder. The text prompt connects with the clicked text encoder. Then the mask prompt connects with the CNN encoder or convolutional neural network encoder. We have the input image, and this basically the heavyweight image encoder, vision transformer, which is processed once per image, and this is of high quality through the image embedding and a lightweight mask decoder, transformer based to the output masks. Basically here, as I said earlier, it is a segment anything, so it will be used in maybe describing or specifying different maybe features in an image, or that will be, or it can be able to differentiate between images. Basically, let's say if there is an image of a dog and an image of a cat, this model may be a trained model, be able to differentiate between a cat and an image of a cat and an image of a dog through training on text to image pairs, maybe a data set of billions of text to image pairs. This model will be able to say either this is an image of a dog or this is an image of a cat. Paper 3 has the visual instruction tuning model. Basically, instruction tuning large language models using machine-generated instruction following data has been shown to improve zero-shot capabilities in new tasks, but the idea is less explored in the multimodal field. So this attempt is to use language only GPT-4 to generate multimodal language image instruction in data. So this one will follow is basically based on following instructions of a user, say an educator, and create a visual image. Basically, the domain-specific problem. The project's problem is the slow or costly creation of accessible educational visuals. While the Lava addresses the limitations of the earlier multimodals, by enabling complex instruction following capabilities with visual context, surpassing models like BIP2, Open Flamingo in tasks. Basically, the earlier models were able to generate visual images, but were limited and costly. And so this is going to be a lightweight. This is going to be a lightweight system, and it will be able to be deployed and work also in offline remote areas. Let's say areas like valley, and also to work on low. We work on low devices, on low-end devices like tablets, smartphones, among others. So this vision instruction tuning model, due to its capabilities, will aid in creation of such a system. So this is the architecture. Yeah, this is the architecture of the visual instruction tuning. Basically, it combines a CLIP vision encoder, the equivalent. This is a simple linear protection layer that aligns image features with the language model's word embeddings. Training is a two-stage process. First, aligning visual and language features, then end-to-end fine-tuning for instruction flow. And this allows the model to understand images and respond to questions about them in a universal way. As you see in the architecture, first we input an image, then it is taken to the vision encoder, then we have the projection layer, language instruction, then the language embedding to the output, the response. Then paper 4, we have the instruct pix to pix. Learning to follow image editing instruction. An abstract, basically, propose a method for editing images from human instructions. Given an input image and a written instruction that tells the model what to do on a particular image, and our model follows these instructions to edit the image according to users' instructions. And to obtain the training data for this problem, we combine the knowledge of two large pre-trained models, that is the GPT-3, the language model, GPT-3, and a text-to-image model, that is Stable Diffusion, and basically to generate a large data set of image editing examples. Our conditional diffusion model, that is the instruct pix to pix, is trained on our generated data and generalizes to real images and user-written instructions at inference time. And this performs edits in forward pass and does not require, example, fine-tuning, inversion. Our model edits images quickly in a matter of seconds, and we show comparing editing results for a diverse collection of input images. Basically, this model will be used in creating a large data set that will be used for fine-tuning other models, or that will be used for training models. And in case maybe, since it is an editing model, basing on users' prompt, it will be able to edit the model according to the way the user wants it to. So the domain-specific problem, basically, the challenge is the costly and expert-dependent creation of educational image sequences. And this instruct pix to pix will address the gap and intuitive variable image editing by enabling fast general-purpose edits without inversion, masks for fine-tuning, making real time applications practical. So this is the architecture of the instruct pix-to-pix pipeline. And basically, first we have training data generation. Yeah, as this model will also aid in also creating creating a data set of an image or an edited image according to users' input. So here we shall have GPT-3 and Stable Diffusion to generate a massive synthetic data set of edited image pairs from text captions filtered with CLIP. And the second step, you see the core model architecture. Here, we have a diffusion model that uses a dual image and text conditioning for line editing from instructions, latent space. Three, we have the classifier free guidance here. We have two separate scales, the SI and ST, which independently control faithfulness to the input image and the text instruction. And before we have the inference, here the model edits real images in seconds from written instructions with no masks, inversion, or fine-tuning needed. The other model we have is learning transferable visual models from natural language supervision. So the abstract state-of-the-art computer vision systems are trained to predict a fixed set of predetermined object categories, and this restricted form of supervision limits the generability and usability, since additional label data is needed to specify any other visual concept. Learning directly from raw texts about images is a promising alternative which leverages a much broader source of supervision. Basically, domain-specific problem, the problem of automating education content generation by transforming a text topic into a coherent image sequence with synchronized narration, which requires semantic understanding, pedagogical accuracy, cultural relevance, and efficiency in resource mapping on text. So this, due to the transferable visual model from natural language supervision, we shall be able to solve the problem of the expertise required to create education content by educators. This from the past content-based curriculum, the National Curriculum Development Center, we shall pass information in the model so that it is able to create education content for the educator to ease the task of for creating a pedagogy which the educators create resources for educating the refugees. And the computation problem involves transforming a natural language topic into a stepwise image synchronized narration using the natural language processing decomposition model, generative image model, implicit alignment, while ensuring low latency, accuracy, cultural relevance, and legal support. So this is the architecture. This is the architecture of our model. The contrastive language image pre-training. Basically, one, we have 4 steps in this. We have the first step is the image encoder, ResNet with modification from ResNet and attention pooling. We have vision transformer with the patch-based input processing, and here the output be a future vector for each image. Second, have a text encoder here which will enable text prompts, and basically this is a transformer based similar to GPT-2, where lowercase byte pair encoding tokens with a vocabulary size of 49,152 bytes, and the output will be a future vector for each text. We have the projection layer with both image and text embeddings are projected into a shared multimodal embedding space using linear projection. Have the contrastive loss for batch image to text pairs for the model computes the cosine similarities between all n-to-n possible pairs, and it optimizes a symmetric cross entropy loss to maximize similarity for correct pairs. So this is a unified multimodal generative. This is a combination of all the 5 models in the 5 papers. So basically, this has a unified multimodal generative and understanding system architecture that integrates the capabilities of all the 5 papers. We have the unit control net, the instruction guided editing, the advanced visual language reasoning. This is built upon a frozen pre-trained text-to-image diffusion core, and which is augmented with shared encoders for visual and linguistic information and suite of specialized interoperable models. These include a semantic spatial understanding module, inspired by segment anything model for segmentation, and a flexible control module that is unit control net, integrating the diverse local and global conditioning signals, and instruction guided editing module that is instruct pix to pix, and a multimodal reasoning module that is LAVA that acts as an the domain space problem. The problem we have in the question, generating context that is accurate and relationship with the culture of the refugees, and that will also help educators create educative content and to forego the huge load of the pedagogy in creating educational content to refugees. Basically, this is the architecture of the unified multimodal. Basically, this architecture is a 5-layer architecture for a multimodal image generation and understanding. Basically, we have inputs such as images, text, and prompts that enter as you see at the top. We have a shared encoding backbone that converts this into standardized embedding. We have specialized modules that perform reasoning in LAVA and segment anything model for segmentation. Basically, the generation core uses these outputs with unit control net adapters to apply precise local and global control based diffusion model, which slices final image. And basically, the final result will be a high quality output that seamlessly integrates all instructions. Basically, this model is appropriate to our project or system since it is through a combination of the multiple models, it is able to enable a prompt, maybe an education topic from an educator, and through its being trained on a large number of data from text to image pairs, it is able to learn and it will be able to generate visual images about a particular topic which will elaborate a given story. So this is appropriate to the system in question. That's all.